So the second one is like E of A E of Aij is equals to Aij, and when I is not equals to R, and E of Arj is equals to Arj plus C times Asj. So this was the second row operation, and the third one is yeah, yeah, R is not equals to S, and the third one is third one is E of Aij is equals to again Ij if I is not equals to R and I is not equals to S, and E of Rj is equals to Asj, and E of Sj is equals to Arj. So this was the third elementary row operations, and we are considering the row operations to be functions, right? So the functions that associates a matrix with the matrix A of size m cross n with another matrix m of size n cross n, right? So now today let us state a theorem to each elementary row. I think I should change this to elementary row operation operation E there corresponds an elementary row operation E1 of the same type as E such that E1 E of A is equals to E of E1 of A is equals to A for each A. In other words, the inverse operation function of an elementary row operation exists and is an
So I suggest that you use an abbreviation ERO because
Yeah.
you are writing it every time. And
yeah, right.
just write ERO.
Elementary row operation, right? Sure. ERO operation of the same type of an elementary row operation exists and is an ERO of the same type. Right. So this is the theorem. So as you can see, this theorem states that for every elementary row operation E, there corresponds another elementary row operations E1, that is actually the inverse of the elementary row operation E, and the E1 is of the same type of E. Okay, so I'm going to prove this for second elementary row operation. So there are three elementary row operations, and I'm going to prove this is for the second one, and you can complete the proof for other twos. Okay. Yeah. So I'm going to define that in here again. So the proof is something. So the second elementary row operation is like E of A ij is equals to aij when I is not equals to r, and E of a rj is equals to a rj plus c times a sj for c c is not equal to 0 and c belongs to the field, right? So this is the second elementary row operation. So for this elementary row operation, since c belongs to f, there is another number minus c belongs to f such that c plus minus c is equals to 0. Right?
Jim,
Yeah, sir.
I suggest that you don't use the word number.
Okay, so an element of the field f. So c is an element of the field f. Okay. So thank you, sir. So
And also here C is not equal to 0. That 0 is not the 0 of the set of real numbers.
yeah,
That 0 is the
belongs to
unique
the
field,
element of
field element.
So I'm considering here the field is f, it is not the real number. So it can be like the field of complex number, it can be the field of real number, it can be the field, the rational number, right? So I'm generalizing this thing. So this is not the 0 of the real number, but this is actually the element of the field f. Okay. So now let us define the operation E1. So E1 of Aij is equals to Aij. So I'm defining the elementary row operation E1. Okay. So this is a definition. So Aij, and if I is not equals to R, and E1 of A Rj is equals to A Rj minus C times A Sj, where R is not equals to S and C belongs to F. Okay. So this is the definition of my E1. So now let us consider.
C belongs to F set minus 0.
Yeah. So I already
Okay.
So C is not equal to 0. So that means actually what Sir was saying is C belongs to the field F set minus 0. Okay. So now let us consider the E1 of E of A. So Ij is equals to, this will be E of A Ij if I is not equals to R, right? And so, and E of Aij is equals to Aij. So that was the definition given here, right? So this is equals to Aij. And now let us consider E1 of E of A Rj. This is equals to E of A Rj Rj minus C E of A Rj.
Sj.
Yeah. Sj. Okay. So this is equals to, what is the definition of E of Arj? So this is given here, right? So this is equals to A of Rj plus C times A of Sj, but this is just simply C A of Sj. Why this is just Asj? E of Asj is just Asj. Why is that? Yeah, so I so yeah, so R is not equals to S. I'm considering R is not equals to S. That means E of Asj is just Asj, right? So that means I'm getting Arj.
But why is it so? Why E of Sj is equal to Asj?
So because R is not equals to S.
Exactly. S is not equal to R.
Yeah. So because R is not equals to S, and we considered it from the very beginning that, yeah. So didn't I define it? Okay, sorry. So R is not equals to S. That's why since R is not equals to S, I'm considering the row R here.
So it's better to say S is not equal to R, not
Okay.
R is not equal to S. Although they mean the same thing.
They-
You please refer back to the definition of E of A.
Yeah.
E of A, they there to inside the block. So
This.
E of A I is equal to Aij
J.
when I is not equal to R. That definition applies here.
Right. So this is so for E of Aij is equals to Aij when I is not equals to R, and I use the same definition here.
Using the same.
Yeah. Right.
Yeah.
So
Since S is not equal to R.
S is not equal to R. Exactly. S is not equal to R. So that's why I'm getting back my original matrix A, right? So for the elementary row operation elementary row operation 1 and 3, you can similarly prove this, right? And it is a very good exercise to do that. So that means for every elementary row operation, there is a inverse elementary row operation that gives you, I mean, the E1 of EA is equals to A. So this is E1 of E of A is just E of E1 of A is equals to A. Okay. So this was the statement of the converse of left side. Yeah. Super. This one?
No, the second one. The second one you did not prove. That's what he is asking.
Okay, so you can do that similarly, right? So this is left as an exercise. You can show that this follows it. Yeah.
So here so we define like E of A RJ, right? A RJ plus C dot A is given.
Yeah.
And then again here E1 A RJ equals A RJ minus C is given. So that is plus and here is minus.
So I say
But we are taking only that part.
no because
we are defining twice.
Jim,
No,
I think
so-
you should have written that define. What is the problem in writing that simple word in the next line, that define? Just spare some time to write things up.
So this is a new definition.
yeah.
This is the definition. So that was the previous one was actually
Original.
one of the types of elementary row operations. There are 3 types. So already that is defined. Now he is defining a new operation associated with that operation denoted by E1. And he is proving that E1, when E1 times E is equal to the identity thing. That means that after E, you apply E1, you change nothing. What is that? What does that mean? It is the inverse of the original operation. That's what he is proving, that if you define the new operation this way, that after application of E would not change anything at all. So you can call that thing the inverse of the original operation. Okay. Does that make sense?
Yeah, it does. So then going down, then we are actually going through this. So it means CASJ still holds, right?
Yeah.
And then, so in this
So-
ARJ, we are taking out
Original
the
definition.
original part. So then it nullifies.
So
So I would recommend that whenever you're defining something, please
okay.
write explicitly that this is a new definition. This is something that we are.
Okay. So now let's.
You are first expanding the E1.
Yeah.
That's why because
So, no,
you also like first evaluate the innermost.
No. So because you see there is a ij here.
I is at the like.
Yeah. So I'm considering the element E of A.
as an element.
Yeah. So ij is the index of E of A, the matrix of E of A. Okay. So that's why on that element I am applying the elementary row operation E1. I mean on that row actually. Okay.
So to answer his question, you see that you won't be able to do what you want to do.
Yeah.
You cannot do first E of A because that ij is attached to E1 of E of A.
So I don't know what is the index inside, right? Because for the definition, you see E of Aij is equals to Aij. Does that answer your question?
Yeah. I understood. I was just clarifying that. You took like the in the bracket it is considered like an element.
Yeah.
And ij is just the index.
Yeah. Okay. So let us define what is it. So definition. If A and B are M cross N matrices over the field F B is said to be row equivalent to A if B can be obtained from A by a finite sequence of ERO, right? ERO is elementary row operations. So this is the definition. So we are saying that if A and B are M cross N matrices, then B is said to be row equivalent to A if B can be obtained from A by finite sequence of ERO. Okay. So yeah, I think it is also so. Yeah, you can show that this is also an equivalence relation. So we discussed something, the equivalence relation in last class, right? So it is also a equivalent relation. So for every elementary row operation, you can show that this relation actually a equivalent relation. I mean, these there are three steps to check what is a equivalent relation, right? So the reflexivity, symmetry, and the transitivity, and you can show that it actually holds for this equivalent relation. Okay. So then theorem. If A and B are row equivalent M cross N matrices over the field F, the homogeneous system of linear equation equations ax equals to 0 and bx equals to 0 have exactly the same solution. Okay. So the theorem states that, so for this theorem, the previous definition is very important. So the definition says that if A and B are m cross n matrices, then we are saying the matrix B is row equivalent to A if you can obtain B from a sequence of EROs on A. Okay. Then the theorem states that if A and B are row equivalent m cross n matrices over F, the homogeneous system of linear equation Ax equal to 0 and Bx equal to 0 have exactly the same solutions. So let me give you a scratch of the proof. So let us consider first that the you can obtain the matrix B from a sequence of ERO on A. So I can write it like A0 to A1 AK is equals to B. So to prove the theorem, what we can do is actually, if we can prove that Aj of x equal to 0 and Aj plus 1 x equals to 0, if these two homogeneous system of equation have the same solution, then we can actually yeah, so we can then so it is enough to show this, that these two equations, these two system have exactly same solution, and we can do it by proof by induction, right? So so now again let us consider the second type of ERO, the second type of elementary row operation. So I'm considering what, that the B can be obtained from A by just the second so B is equals to E of A, where I'm considering E as the second type of ERO. Okay. So B ij is equals to just E of Aij and this is equals to Aij if I is not equals to R, right? This was the second elementary row operation. So not this actually, so and B I1 B IN, this will be what? So this is just 0 times A11 A1n plus 1 times AI1 so, right. So yeah, so Bij is equals to E of Aij, and right. So for this row, Bi1 dot dot Bin, this is actually what then? This is just the 0 times A11 dot dot A1n plus, so this is actually what? This is the linear combination of the rows, right? And I'm multiplying this AI1 to AIN with just 1. So this gives me this condition, right? Is it clear or?
Sorry.
Okay, so
So you just expanding this equation into the following one.
I mean, so Bij, it is just a element of the matrix, right? Okay, so I'm considering the row of the matrix B, ith row of the matrix B. Okay? Yeah, so I'm multiplying 1 with this.
So 0, 1, these are arbitrary numbers.
No, 0 is just the entry coming from the field.
Well, I can take any value.
No, so this is like Bij is equals to what? This is defined as Bij is equals to E of Aij. Okay, and this is equals to Aij. So now I am taking the ith row of B. So okay.
ith row of B is equals to ith row of A.
So this is
B11, but those combinations are 0. Only we take the
B1n. Okay, let me clear this up. Then so Bi1, Bin, B, M1, Bmn, right? So I'm considering this row. Okay. So this row starts from Bi1 to Bin. So now if this condition, so the condition was Bij is equals to E of Aij, right? And this is equals to A of Ij. So J starts from 1 to n, right? So what is Bi1? This is just E of I1, and this is equals to AI1, right? So, and that is just what? I am just multiplying this ith column of A by the number, by the entry element 1 coming from the field F, right?
Always.
Yeah.
There is a small mistake that the plus sign will be left of zero at the last row.
Oh, yeah. So then for Brj, this will be equals to E of A Rj, and this is equals to, what is it? Yeah, Arj plus C times A Sj, where R is not equals to S. Okay. So now, what will be the row R of the matrix B? B R1 B Rn, right? And this will be equal to, so 0 with A11 A1n plus 1 AR1 ARN plus C A S1 ASN right? So that means so I can write the row BR1, I can write the rth row of matrix B in this fashion, right? So the what I am actually doing here, I am taking the linear combination of row rth row of A and S row of A, right? Okay. So that means, and we defined it, that is the definition. So B is equals to E of A. Now, so Bx equal to 0. So each equation of B is actually the linear combination of the equation of Ax equal to 0, right? Is that clear? Why the Bx equal to 0 is the linear combination of the system Ax equal to 0? Because from this you are seeing that this, and from B this, sorry, this and this, right? So that means Bx equal to 0. So each equation of Bx equal to 0 can be expressed as a linear combination of equations in the system Ax equal to 0, right? Okay. So
I think this goes back to the theorem that we proved yesterday.
Yeah.
That the linear combination is also a solution.
yeah, but now what I'm going to show you, that we just proved in the previous theorem, what we proved. For every elementary row operation E, there exists of the same type another elementary row operation E1 that is the inverse of that operation E, right? So that means I'm getting this equation Bx equal to the system Bx equal to 0 from taking the linear combination of the system Ax equal to 0. So in the same way, there exists a E1 of the same type, right? That can give me the system Ax equal to 0, and this Ax equal to 0 will be what? That is the linear combination of the system Bx equal to 0, right? Using the previous theorem, what we can say is that this, so in the last class, we said something like there was a theorem, the theorem was,
The linear combination of the system.
yeah. So equivalent system of linear equations have exactly same solutions. Okay. So there was a theorem system of linear equations have exactly the same solution, right?
Did you define what it means by equivalence?
Yes, sir. In the previous
class?
class, yeah.
What was that? Can
So-
you recap?
Yeah. So the equivalent system of linear equations. So if two system of linear equations are said to be equivalent if each equation in each system can be expressed as a linear combination of the equation in the other system. So this was the definition. So two system of linear equations are said to be equivalent if each equation in each system can be expressed as a linear combination of the equations in the other system. So, and in this proof, what we already showed that Bx equal to 0, this system is a linear combination of the system Ax equal to 0, right? And from using the previous theorem, we just proved that there exists a elementary row operation E1 corresponding to this elementary row operation E that is inverse of that row operation, right? So Ax equal to 0 can also be, I can construct Ax equal to 0 from the linear combination of the system Bx equal to 0, right? So that means these two system is actually,
I have a question.
yeah,
In the last class, we have defined equations m cross n, let me say m cross n matrix to k cross n matrix, right? As a linear combination.
okay, yeah.
So then we stated that the solutions of that second case, a k cross n matrix, is may not be a solution of the previous one.
Yeah.
But
In this theorem, what I started with that if A and B are row equivalent M cross N.
No, what he is suggesting that in the last class, you did not quite define equivalent system of linear equations. You just showed that if a system of linear equations have certain solutions, then if you take an arbitrary linear combination
Yeah.
of those equations of the system and form another system,
Yeah.
the new system
That new system can have other solution
other solutions.
that may not be the solution of the original
Exactly.
system. Yeah.
But
So-
in your case, it's a stronger situation
Yeah.
where each equation of one system can be expressed as a linear combination of the
other
other
system.
system and vice versa.
So that's why I'm considering the M cross N matrix. So I'm taking M linear combinations of the, so I'm constructing M equations of M equations from the linear system AX equal to 0, right? And again, I'm constructing M equations from the system Bx equal to 0.
that means k must be equal to m
Yeah.
in the previous class.
Yeah.
So
That's why these two systems are equivalent to each other, and if two systems are equivalent to each other, then they have exactly same solutions. Okay.
I have like now the theorem that you say the equivalent system of linear equations have exactly the same solution. I don't think we proved that, right?
We just proved here, right? So
No, you just stated
Yeah.
it. You don't
We
prove it.
use this
Okay.
theorem now.
Yeah, so-
to prove,
So from here, you can see each equation of Bx equal to 0 can be expressed as a linear combination of the equations in the system X equal to 0. And so this was like B equals to E of A, right? But in the previous theorem, we found that there exists E1 E arrow of the same type of E such that E of E1 of A, right? So this is equals to A, right? But I started from, and this is also equal to what? E1 of E of A is equals to A. But I started B is equals to E of A. So if I take E1 of B, this is equals to E1 of E of A, and this is equals to A, right? Do you have any confusion?
No. I understood that.
Yeah, so-
A and B are here.
Okay, let me finish. Okay, so
I think in previous class you said that we will prove it to this class that if two systems are equivalent, then they have the exactly same solution.
yeah, so I'm showing that. So that means that AX equal to 0. So A is equals to what? E1 of B, right? So that means AX equals to 0. This system is consists of equations that are linear combination of the system Bx equal to 0, right? Right? Yeah, so okay, so now I'm using this theorem that equivalent system of linear equations have exactly the same solutions, and this follows from this argument that two systems of linear equations are said to be equivalent if each equation in each system can be expressed as a linear combination of the equations in the other system, right? Does that answer your question?
Yeah, I understood, but if I recap that, you're saying that two systems of linear equation, two systems of linear equation are, we can call them equivalent if, for one system, every equation can be expressed as a linear combination of the
Other
other system, and vice versa, that those systems are equivalent.
Yeah.
My question is that now also here we are first proving the theorem that for row equivalent two matrices.
I mean, the two matrix A and B is row equivalent to each other. So if a matrix B can be obtained from the matrix A by finite sequence of elementary row operation, right?
Yeah.
So we proved it in the previous theorem. Okay. Then
Like I'm just what is that? Which theorem are we proving here? We are proving that for row equivalent matrix A and B.
Okay, yeah.
That Ax equals to 0 and Bx equals to 0 have the same solution.
Exactly. Same solution.
But while proving this, we are also saying that Ax equals to 0, Bx equals to 0 are all, these are also equivalent systems.
Yeah, of course.
And as equivalent systems have the exact have
Solution from the previous lecture.
Yeah.
There's theorem that equivalent system have exactly same solutions. We're using two theorems to prove this theorem. Okay. So,
but my question is that we for equivalent, if two systems are equivalent,
yeah,
their solution is the same.
Yeah.
We never proved it before.
No.
But we are using. I was just saying that we are using the theorem as.
So in the last lecture, what I showed that for a system of equation, you can take a linear combination of that system of equation, and yeah.
I was saying that whether that we can this theorem can be proved like that. For example, we have a set of equations, and we take a linear combination and make another system, and this system will have the solution of the first system, right?
Yeah.
And we can also do it like vice versa, whether if we have a system and we make another system, and we can say that this system, the solution of the first system is included in the second system, and when we do the opposite, the solution of the second system is also included in the first system. So we can say that equivalent system has the same solution.
Exact same solution.
I was saying that whether this is the proof.
Yeah, this is the proof, right? But in the previous, what Sir was saying, like if you take a linear combination, arbitrary linear combination of the first system, Ax equal to 0, there might be some solution in the new system that are not the solution of the original system, Ax equal to 0. But if these two systems, Ax equal to 0 and Bx equal to 0, if these two systems are equivalent to each other, then the solution will be matched. Okay. Is that clear?
I think for those systems, the operation ERO is not the relation ER1 does not hold.
I mean, the ERO is only, I'm considering the ERO for the matrix, right?
Yeah.
I can apply ERO on system of equation.
And when the matrix of that system.
Yeah. Right. And it is, so we have to consider it to be a homogeneous system. Okay.
You cannot do this for
I mean, if the inhomogeneous system can not have a solution, because there is a trivial solution for the homogeneous system, right? The 0. But for inhomogeneous system, it is not true that the system is always have a solution. Okay. So, so let me give you an example of this. Let us consider example.
Yeah, we finished the proof by induction, right?
Yeah.
But induction means doing the same thing again and
Again.
again, right? That means we can only do this for if we take an ERO type, we are taking ERO type 2, right?
Yeah.
Second operation. That means we can only prove this for ERO type 2s again and again,
Yeah.
not other EROs.
Yeah, you can also consider the other years.
No. Say if I take operation type 2, then operation type 3, then operation type 1, can we prove it?
In the
Yeah,
same
of course.
sequence, can you take
Yeah.
different errors?
Yeah, of course, you can do
I think
that.
that's possible.
Because there is always a inverse operation. Right? So what is it is like you are taking a elementary row operation, then you are taking another elementary row operation, then you have to take the inverse of the second operation first, then you have to take the elementary row operation of the first step.
It's like putting on stack, right?
Yeah.
Unstack the same way.
Okay. Okay, so let us consider an example. So A is equals to 2 minus 1, 3, 2, 1, 4, 0, minus 1, and 2, 6, minus 1, and 5. So I'm considering A is a matrix of this type. So this is 3 cross 1, 2, 3, 4. 3 cross 4 matrix, right? So yeah, so let us first we can apply elementary row operation in this matrix, right? So first let us consider the elementary row operation. Minus 2 R2 plus R1 is equals to R1 prime, then minus 2 R2 plus R3 is equals to R3 prime. Okay. So I'm taking this elementary row operation, and this will give me, this is 0, and so 2 times 4 is 8 with the minus, that means minus 9, then this is 3 and 2, this is 4. And the second row is unchanged, this is 1, 4, 0, minus 1, and the third row is 0. So 4 times 2, that means 6 minus 8, that is minus 2, that is minus 1, and that is 2, that is 7. Okay. Then so minus 1 over 9 with R1 is equals to R1 prime, then this will be like 0, 1, minus 1 over 3 and minus 4 over 9 with 1, 4, 0, minus 1, 0, minus 2, minus 1, 7. Okay. So these are all illuminated row operations that are allowed, right? Okay, now take again. So, right. So minus 4r1 plus r2 is equals to r2 prime, and minus, right, 2r1 plus r2 is equals to, sorry, r3 is equals to r3 prime. Then this will be 0, 1, minus 1/3, minus 4, 9, and this is 1, this is 0, and this is, right, 4, yeah, this is just 4/3, and this is just 7/9. Yeah, and for the last row, this is 0, 0, and so I'm multiplying 2 minus 2, 3, minus 1, this is 2 minus 1, this is 3. Yeah, so this is minus 1 with 11/3. Okay. So now what I can do is, yeah, so minus 1 times r3
Why
equals,
did we choose these set of elementary row operations?
so I'm going to discuss it in the next section.
Yeah.
So yeah, there is a reason I'm doing this.
That is a natural question to follow. Why did we choose this set of?
So
That he is going to answer. So
yeah, so minus r3 is equals to r3 prime, then this is 0, 1, minus 1/3, minus 4/9, 1, 0, 4/3, 7/9, and 0, 0, 1, 11/3. Okay. So now if I multiply, so 4/3 minus with r3 plus r2 equals to r2 prime, and 1, 3 r3 plus r1 equals to r1 prime. So that means 0, 1, 0, and it is 11/3 times 3, that means 11/9, minus 4/9, 7/9. Yeah. So this is 7/9, and the second one is 1, 0, 0, 7/9, minus 11/3, 44/3 is equals to 9, 7 minus 44, that is, minus 37 over 9. And the final row is 0, 1, 0, 1, 11 over 3. So finally I am getting this matrix, right? So I started from the matrix A equals to this, and after taking this elementary row operation, I end up with this, right? So now if I consider AX equals to 0, and if I just this is, let us consider R. So from the previous theorem, we can conclude that AX equal to 0 and RX equal to 0, these two systems has exactly same solutions, right? So that means, yeah, what was that? So the system AX equal to 0 is actually the system AX equal to 0 is 2x1 minus x2 plus 3x3 plus 2x4 is equals to 0, x1 plus 4x2 minus x4 is equals to 0, and then 2x1 plus 6x2 minus x3 plus 5x4 is equals to 0,
Yeah.
right? And for the later matrix R x equal to 0, that this system 0 correspond to the equations x2 minus 5 over 3 x4 equals to 0, sorry, what was that, 7 over 9 x4 equal to 0, then x1 plus, sorry, minus 37 by 9 x4 equal to 0, then x3 minus, okay, so 11 over 3 x4 equals to 0. So these two system has exactly same solutions. Okay.
I have
Now,
a few comments to make.
yeah.
So if you go up a little more, so try to find a pattern here. We are looking, so
Yeah,
look at the ones present in this matrix,
So-
and try to look at the columns where these ones are present. And in those columns, except for these ones, everything else is 0, right?
Right.
So this is some structure that is an ideal structure that we want to achieve, okay? And that he will explain later that what is it called, what is this structure called. But why do we want such structure? That is another question. So we'll see later that this facilitates the finding of the solution of the original system, because we are reducing our system to in such a form that we can easily find the solution having a look at that reduced system. Okay, and so having a look at this system, right away we know what the solution is, and the crux of the matter is that these elementary row operations don't alter the set of solutions of the system. So these are such operations. By applying these operations, we don't alter the set of solutions of the original system. So that is the most important thing. So while Ax equal to 0, so that system has the same set of solutions as the set of solutions of Rx equal to 0. But by looking Rx equal to 0, we can immediately see what the solution of the system of equations Rx equal to 0 had. But from the previous theorem, we know that the set of solutions of these two systems are the same. So we have the solutions.
So, so that's why I wrote all these equations here. So now, if you just look at this system of equations, so it is not easy to say that what is the solutions of this system of equation here, right? Because this is a complicated system. But looking at this system, you can easily say that x2 is equals to what? This is just 7 over 9 x4, and x1 is equals to minus 37 over 9 x4, and x3 is equals to 11 over 3 x4. So we'll come to this, that there are some these variables that x4, these are called the free variables, and so x1, x2 and x3, these are called the leading variable. So we'll come to that. But so what sir was saying is, after applying some elementary row operations in this matrix, we are getting this matrix, right? So, and from the previous theorem, we know that since these two systems are equivalent to each other, that means the solutions of these two systems are equivalent, right? So that means although we do ERO on this matrix, but the solution does not change, right? Okay. So now take a look again in this matrix. That so for this row, the row 1, the first non-zero entry, so this is a non-zero row, right? So there is some entries here and here that are not zero. The first non-zero entry is 1. In the second row, the first non-zero entry is again 1, and in the third row, the first non-zero entry is again 1. And also there is another pattern that when the first non-zero entry of a row is 1, that is also called a leading row. So, leading 1. Yeah, so, but when the leading 1 is happening in a row, on that column, these columns, you see every other element in this column is 0, only the leading one is there. Similarly, you can also see that this is also, and here is also, right? So now we come to the definition of
Can you please read again when the non-zero entry is 1?
Yeah.
So what do we call it?
the leading one. I'm going to define that. Okay. So definition: N M cross N matrix R is called row reduced if the first non-zero entry in each non-zero row of R is equal to 1. Then the second condition is if each column of R which contains the leading non-zero entry 1 of some row has all its other entries 0. So the first one is A. The first non-zero entry in each non-zero row of R is equal to 1. So now let us compare this with this matrix R. The first non-zero entry in each row, so this is the first row, right? And the first non-zero entry is this. This is 1. And the second condition is each column of R which contains the leading non-zero entry 1 of some row has all its other entries 0. So again, as you can see, all the other entries in this column, this is this and these are just 0. Similarly, for the second row, the first non-zero entry is 1 and all the other entries in that column is 0. So that's why so these metrics are called row reduced metrics. Okay. So what are the other examples of row reduced matrix? Can you give an example of row reduced? Yeah, the identity matrix. N cos n identity matrix is also a row reduced matrix. It is not just row reduced matrix. We will see that it is also a row reduced echelon matrix. Okay. So finally, there is another theorem. Every m cross n matrix over the field here is row equivalent to a row reduced matrix. So we're not going to prove this theorem, but so the idea is, so let me consider a simple matrix, that is, let us consider 0, 0, 0, 1, star. Then some number, let's say C, where star denotes the unknown entries in this matrix. Yeah.
The non-zero row
Yeah.
means there will be at least one non-zero element, including the leading one.
Yeah. So it is possible that all the entries can be 0. Okay.
That is called a zero.
0. Yeah. So
Star cannot
that's
be
why I say for every non-zero row. Okay.
including the leading one. Right?
Yeah. Okay. So this is a general example. So I'm considering this matrix, and I'm considering here. So if this matrix is just like this, zero, then as you can see, it is a 0 row, right? So I don't have to do anything for this row because it is already 0. So now if it is not 0, so the way I did it in, let's consider this is a C and these are some other numbers. Okay, so star represents the unknown elements here.
Non-zero.
Non-zero, yeah. So in the first row, the first these entries, let me change my color. So these entries and all these entries are 0, I'm considering. So I started with a 0 and there is another 0. Okay. So, and I'm considering this is the kth column, and the first non-zero entry in this non-zero row is this C. So to make it a row reduced matrix, what I need to do?
Make this one.
Yeah, make this 1. So how can I do that?
We can use the 1 by C multiple with this
Why 1 by C exists?
because C exists in the field.
Yeah, because C is an element of the field, so there is an there is a element 1 over C, and I can multiply it with this. Okay, so that
And
means
by the way, there is a correction that stars can be 0 as well. They are
Yeah.
not all non-zero. They are unknown.
Yeah.
They can be 0 or non-zero. We don't know.
okay, sorry. So if I take the elementary row operation of the first type with 1 over C type, it's R1 equals to R1 prime, then this will be, so 0, 0, 1, and then star, star. Okay, right? Then what I can do is for I is greater or equal to 2, I can take this row like so minus A ik times R1 plus Ri is equals to Ri prime, right? So then this matrix will be 0, 0, 1, star, star, star,
if the star under the 1 in the first row is already 0, then we don't worry about it.
Yeah.
We don't have to do anything. If that is non-zero, then we apply this operation to
So-
make that 0.
Yeah, I said that. So in the first thing, I considered that this row is just 0. If this row is just 0, then I don't have to do anything.
Which row is it?
So, sir, it was, I erased it. It was like, I considered it like 0, 0, 0.
No, I'm
Then
not
I-
saying about that row. I'm saying the star just below 1 in the
Okay.
second case.
Yeah.
If that is already 0,
Okay, okay.
we don't need to do anything.
Yeah.
But if that is not 0, then we do that
Yeah.
operation.
This. Right? Yeah.
Should we guarantee making this 0? But this column,
Yeah.
Yeah.
Only for that
But-
column.
not the row.
No, not the,
So this column.
yeah.
So you can make everything underneath 1 0
Zero.
by
By-
that kind of operation.
Right.
So then again, for the second row, what will be the situation? It is possible that the first few stars can be 0, or even the first star can be a non-zero element of the second row, right? So the first entry that is not 0, what I can do for the second row is I can take the first elementary row operation, what I did here, right, in the second row as well, to make it a leading one. So for that case, this will be, so, and there is actually two situations, but let me write the first one is, so I'm considering this to be 0, 0, 1, star, star, then, so let us just consider this, and this is kth column, okay, and let me consider this is, so I'm taking a first type of elementary row operation in the second row here. So this will be what? This is 1, and then this is a star, this is a 0, star, star. So I'm taking a first type of elementary row operation in this matrix, and I'm saying that this is the k prime column. Okay. So then again I can do what? I can take this type of elementary row operation, right, in here, but in this the I runs from what? Yeah, I runs from 3 to m. Okay. Then another situation can be arise that it is possible that 0, 0, 1, star, right? So for this, k prime is less than k, and for this, k prime is less than k, and here k prime is greater than k, right?
So denote the K in this matrix.
Yeah, k, and this row is k prime, right? And applying this operation again and again, I will end up with the row reduced matrix, right? Is that clear? Or if you have any confusion, yes. Yeah, do you have any question?
Yeah. And
So what is that?
the second case, the first.
We have to start. So there will be another operation like minus a1 k prime r1 plus r1, sorry, r2 plus r1 equals to r1 prime, to make this entry 0. Okay, this entry, right? Because in the row reduced matrix, the definition in the row reduced matrix that the column, only the leading one is the non-zero entry and all other entries are 0, right? So I have to
Again, if that star is already 0,
Zero,
we
then
don't
have
care
to.
about it.
Yeah. So okay, and there are some examples you can do from Hoffman and Kunz. Page yeah, page 10, problem 1, 2, 4, and 5. Okay.
So,
Yeah.
you have created a generalized equation to make all entries 0 above the leading 1
Yeah.
and below. So, there is any generalized equation to create the leading 1 in a row. Right?
Yeah. So I did it in here. So the first entry was non-zero entry was C here. So I have to take the inverse, multiplicative inverse of C, and I can multiply it with the row R1, right? And this will give me what? This C will be just this one, right? And why the multiplicative inverse exists? Because C belongs to F. C is an element of the field, and in the definition of the field, that for every non-zero element in a field, there exists a unique inverse, multiplicative inverse of that element, right?
So, what about the other rows?
Yeah, so I took the same thing here. So let's consider these entries to be some k. Okay, so here what I did is 1 over k times R2.
Let us call it something else. K already you have used.
Okay, sorry.
C, B, D, there are many other letters.
Yeah, sorry. It is like B. So I can take, actually what I can do is I can give you a generalized formula for if,
My question is if
yeah, so I'm going to answer that question. Just give me a second. So if A ik is the first non-zero entry in the ith row, then how can you make it to 1?
No, my question was if it is not a fast non-zero,
Yeah.
there is other elements.
Before that? Okay, so that was not I'm considering. If the first entry that is non-zero is that entry,
Okay.
if it is possible, so as I started that this entry can also be a non-zero entry, right? So star is so star can be a 0 and non-zero entry as well. So if it is 0, I don't need to consider it, right? So I look for the non-zero entry in the second column, then in the third column, then in the fourth column. So the first non-zero entry that I have to make 1, right? Does that answer your question? So okay, I think I can give you an example. Let us consider 0, B, 2, 6, 8, 0, 1. Something else. Let's see. 8, 4, 3. So do I need to consider this 0 in the first place? No. So what I can do to make it a row reduced matrix, I have to multiply row 1 by 1 over b, right? So for the second row, this is what? This is already the first non-zero entry is 1, right? Do I need to do anything with this row? And for the third row, what I need to do?
1 by 2, multiplied by 2.
Right. So, but after making this b 1 over b, this will be what? 0, 1, 2 over b, 6 over b, and 8 over b. But to make this a row reduced matrix, what I need to do? Every entry in that column have to be 0. So this entry will not be 2 here, right? So is that answer your question?
My question is if consider the 1, the second row.
Yeah.
Are we applying the operation for 1 over b for the third row, because we have stated that when we have 0 we don't need to apply it.
B is not a 0.
The line, entire line is 0. So if we have already 0, then we don't need to apply the row operation.
Yeah, I don't need to apply it for the third row.
Yeah. So
Yeah.
it will be 2.
Yeah, but right. Sorry, it can be generalized, but it's something else. Let's say 1 here. Right?
Then it is the leading.
Yeah. So no, this is not the leading one.
You have to make the
Why isn't that the leading one?
It can be a leading one, but what he
It's the leading one.
yeah. So I can also make B the first row a leading one by divided 1 over B. So it is so just okay. So this is some other number. Let's say Q.
Okay.
So-
If you make B a leading one, then
Yeah.
Q is no longer a leading
Yeah.
one. That's correct.
Right?
In each column, there can be one leading one.
Yeah.
Okay, so if that's completed, then I have to, I need to make a comment on something. So last class, you gave an example of two equations forming a system of linear equations, and you took the linear combination of those two equations to form another equation. Do you have that example?
Yes.
Can you please write that example? That's a very simple example of two equations.
Sorry, it was in the bag. I have to.
But you guys have it, then please tell him the equation. So it was a system of two linear equations.
2x plus y equals to 3. Then
And what is the other one?
equals to -1.
Okay, so this is one system, and what is the other system that you took as a linear combination of these two systems?
Okay, I took a linear combination of so 2x plus y equals to 3, and 3x minus 2y is equals to -3, and I take a linear combination, so this is 5x minus.
No, why is 3x minus 2y equal to -3?
I'm making it a homogeneous system. So
No,
is that
what is the starting point? What is the starting system? 2x plus y
Yeah.
equal to 3, x minus 2y equal to -1? That
Yeah.
one?
yes,
Okay, now you take a linear combination of these two equations.
arbitrary linear combinations.
Okay, take.
So this is just simply some a 2ax plus ay plus bx minus 2by equals to 3a minus b.
Yeah, take some
Number.
with, to make it simpler.
Okay, so let it multiply it by
Just add these two equations. That's it. 3x minus y
3x minus y
is equal to 2, not minus 2,
Yeah.
plus 2. Yeah. Okay, now can you put blocks in the two systems? That is one block, and this is the other block. Okay, call the first system 1. You don't have to write system 1, just write 1 and 2.
Okay.
Like you numbered it. Yeah. System 1 and system 2. Okay, now can we say that the
This is-
solution of system 1 is a solution of system 2?
Yes.
We can, right?
Yes.
But we cannot say that all the solution of system 2 is a solution of system 1. This is what we studied in the last class.
Yeah.
But I think you did not go further in the last class.
Yeah.
So which was a misconception, a confusion generated during the class lecture. So why does it happen that any solution of system 2 is not a solution of system 1? Why does it happen? Do you understand my question? Why is it the case that any solution of system 2 is not a solution of system 1?
Yeah, I think you gave us a simple answer, like the geometric answer, because the second system is basically a line that has a lot of points, but the system 1 is
No.
maybe
Yeah, but in the flavor of the theorems that we studied, can we explain why a generic equation of system 2 a generic solution of system 2 is not a solution of system 1? Because can you write each equation of system 1 as a linear combination of the equation of system 2? First of all, what does it mean by a linear combination of equation of system 2? Because there is just one equation. So by a linear combination, I mean just multiplication of equation of system 2 by any real number, right? So now, can you produce each of the equation of system 1 by multiplying a number with the equation in system 2? Just check.
6 plus y. Change this. 6 plus y.
Yeah, 3x plus y equals to 3.
So
Is it possible?
You
Yeah.
can write 3x plus y.
But if it is written 2x plus y.
2x plus y?
Yeah.
So-
In the last class, it was written 2x plus y equal to
Yeah, but just consider this
3.
system. Yeah. So now
Okay,
my
sorry,
question is, if I start with the first equation,
It was written 2x plus y.
okay, then okay, then
So-
this is 3x minus y is equal to 2. Okay.
2x plus y.
Now 2x plus y is equal to 3. Can I get it by multiplying any number?
Arbitrary number k with 3x minus y
equal to 2.
equals to 2. So, just consider it this way. 2.
Why is it like that?
No, sorry.
Come on. Yeah.
Is 2k.
To 2k, yeah, exactly, right. So, is there any k that satisfies this?
So, we want to go here to there. So, what you need to do
is
is
there
you
any
have
k
to.
that
yeah.
will produce this
3x plus
thing?
y equal to 3.
So, suppose that we want
What
to
is that
make
k?
the coefficient 2, then we have to choose k to be 2 over 3, right?
But
But that 2 over 3 will alter this 2k, that won't be equal to 3. And also the coefficient
of y.
of y will be something else. So that tells us that, now go back to your, that tells us that I cannot write an equation of system 1 as a linear combination or as a multiple of the equation, forming system 2.
Right.
So which means that these two systems are not equivalent. So when we say that two systems are equivalent, each equation of each system can be written as a linear combination of the equations of the other system,
Yeah.
which is not the case here.
And for the equivalent system, the case is x1 equals to 1 and y1 equals to 1. So now consider system 3
What is system 3?
with system 1.
No, there is no system 3.
No, I'm just, sir, if I take the row reduce, if I solve this system, I will get x1 equals to 1 and y1 equals
all
to
right.
1.
So that is the the row reduced
Yeah.
form
So,
property, right?
So what I did for 2x plus y equals to 3 and x minus 2y is equals to, yeah. So now if I extract the matrix equation, this will be what? 2, 1, 1 minus 2. This as A matrix. Then, and here x is just x, y. And although we didn't solve the inhomogeneous system, but still y is equals to 3 minus 1. Right? So this is equals to what? Ax equals to y. Right?
Yes.
So as you can see, I can apply elementary row operation on A with actually on the augmented matrix, but we still didn't define it.
Yeah, so
Yeah.
I think we can discuss it later,
Yeah.
because we did not
Yeah, so
introduce the concept of augmented matrix. But the whole point was that with this example in the back of your mind, you can see that what are the implications of the theorem that you studied today. Okay, so whenever you have two equivalent system of linear equations that they have exactly the same solutions, and we apply that theorem to reduce our system to a row reduced,
row reduced matrix of the,
to a simpler system that gives us the solution easily.
Yeah.
Okay, all right. So that's what I wanted to say.
okay, thank you very much.
Sorry, last
Yeah.
I think sir asked a question.
Okay, I think we discussed it.
Oh, sorry, I think I missed it. Can you say it again?
Okay,
The same group, or the it's not in the group, right? It's in the art, Michael art.
yeah, that was from the
Chapter one.
chapter
Chapter one.
Artins.
The second one that you mentioned.
No, the first.
But here this is the second group.
This is the second
Today's one.
Yeah.
Chapter.
Today's this one is for problem Hoffman and Kunz. Okay.
Yeah, but in previous class, the example.
I didn't.
Yeah.
Chapter one.
Did you find this?
Chapter one, I just saw the number, but 2 is still not there. These are numbered as 1.1, 1.2.
Yeah, this is number one.
Okay. Actually, that is the number one.
Can I say a few things? Some of you, for the other class, some of you requested extra classes. So extra class.